what we're going to do is we're going to look at some FRQs, and there's different types. Like the first FRQ is a torsional pendulum. Okay, so we're going to just set up the first half of this one right now. So it says a torsion pendulum, so they're telling us what type of pendulum it is. Shown above consists of a disc. So because it's a disc and it's rotating around this axis, which it shows you in the picture, we know it's going to have a moment of inertia. It's suspended by a flexible rod attached to a rigid support. So what they're telling us is the mass of the rod, doesn't matter. When the disc is twisted through a small angle, the twisted rod exerts a restoring torque. So remember, the restoring torque brings it back to its equilibrium position that is proportional to the angular displacement. Tau is equal to negative beta theta, where beta is a constant. The motion of the torsion pendulum is analogous to the motion of a mass oscillating on a spring. In terms of the quantities given above, write but do not solve the differential equation that could be used to determine the angular displacement of the torsion. Okay, so you're reading this problem, you're like, where do I start? Okay, so what happens is with this problem, where you're going to start is you're going to look at what you're reading. And you're going to say, first of all, again, as you're reading it, you're going to just think about certain things that are important. So the first thing they tell you is, they tell you that tau is equal to negative beta theta. And the thing is, when you think about tau in general, and you go back to when you did rotation, right? There were two things that we did with rotation. We said that tau is equal to FR, torque is equal to the force times that perpendicular distance, and we said tau is equal to I alpha. Those are the two things we learned before for rotation. So now this is rotating, and the thing is, they tell us that tau is equal to negative beta theta, but it says in terms of the given quantities above, write but do not solve the differential equation. So differential equation tells us we're going to be using calculus. But they want us to solve for theta. Is theta anywhere even in here? No. But what's going to happen is we're going to do the same thing that we did before with this, saying when we had tau and tau, we set these equal to each other. So when we look at this now, we know tau is equal to FR. Well, and we also know it's equal to I alpha. So tau is equal to I alpha. And then we also know that tau is equal to negative beta theta. So instead of FR, we have negative beta theta, and then we have torque is equal to I alpha. Because we're solving for theta, and we know they want the differential equation, we know that alpha is equal to d squared theta dt squared. Do we know that? Yes. We know that the second derivative of theta gives us alpha. So now this is how I get rid of this alpha and have it in terms of theta, and this is how I'm going to have my differential equation. And that's going to be equal to negative beta theta. And this is all you have to do for part A on this FRQ. You're not solving it. You're not rearranging it. This is a differential equation because it has d squared theta dt squared. And is this in terms of only the variables I have here? That's it. All right, so that was part A. For part B, it says, using the analogy of a mass oscillating on a spring, determine the period. So before I even read on, okay, it says using that analogy. So what is the period for a mass oscillating on a spring? T is equal to 2 pi times the square root of m over k. Is that the period for the mass on a spring? Yes. So it says, using that analogy, find the period of the torsion pendulum in terms of those quantities. So T is equal to 2 pi. Now I'm going to say to myself, what's analogous to mass? I, moment of inertia. Now I'm going to say, what's analogous to K? Well, K is the constant. What's the constant here? Beta. And that's it. That's actually worth 3 points. That is worth 3 points. So what you might think is the hard part of question number 1, it's not really that bad. And the rest of this problem is actually, you're drawing a graph, you're drawing a best fit line, you're finding the slope, you're doing y is equal to mx plus b. So that is this is the torsion pendulum. Okay, so now we're going to move on to the physical pendulum. So if you look at this rubrics, this is 2011 M3. They actually have what we did here. And then this is the alternate solution. But because they're telling you it's analogous, to just write this and this is much easier than doing all this. Does everyone see what I'm saying? And they're telling you it's analogous, and they give you full credit for that. So that's a much easier way to do it, isn't it? All right, so let's go on to the next one, which is the physical pendulum. So number 2, this is a physical pendulum. And again, when you're reading these questions, make sure that you are doing it in terms of the variables that they ask for. So you might want to say, oh, it has to be big M, it has to be L, it has to be the moment of inertia, and then like a constant would be G. So as you're reading the problem, circle all those little things. So this says you're given a long, thin rectangular bar of mass M and length L with the pivot attached to one end. The bar has a non-uniform mass density. So because the mass density is not uniform, even though it looks uniform in the picture, what they're showing you here, it says the center of mass is located at a known distance x. So is the center of mass in the middle? No, because it's non-uniform, even though it looks uniform in the picture. So anyway, it says you would determine the rotational inertia I sub b of the bar about the pivot point by suspending the bar from the pivot as shown and allowing it to swing. Express all answers in terms of the quantities and stuff like this. So now it says by applying the appropriate equation of motion to the bar, write the differential equation for the angle theta the bar makes with the vertical. So what I would do personally is I want to conceptualize the picture. Because now my bar is moving up. So here's where the bar started. That's going to be my frame of reference. And now the bar is going to shift like this. Now, they told me the center of mass. It's actually not in the center. It's at a certain distance, x, from here. Okay? And then the length of the bar is L. So this is my angle here, theta. So again, it says by applying the appropriate equation to the motion of the bar. So the bar is moving, write the differential equation. So again, my sign convention, summation of tau is equal to I alpha. So what is... I have I alpha, and then I'm going to have here, I'm going to do it the way I'm used to, but then I'm going to substitute in the variables they have in this problem. So this is equal to, I have FR is equal to I alpha. So to get a differential equation, I know I'm going to take alpha, and for that part, and now I'll substitute in, the I needs to be I sub b, and I know that alpha is the second derivative of theta, so I'm going to substitute in here d squared theta over dt squared. So now that second half of the equation is set. Now, according to my sign convention, here's my force. So when I'm doing the force from this distance to the axis of rotation, because counterclockwise is positive, that's going to be negative. So my force is going to be mg sine of theta times the distance. Well, it should be mg times x sine of theta. The x goes really in front of that, but I'll rewrite it correctly later. So it's that distance. Remember, here's my force, and then this distance here, that's the distance to the axis of rotation, is x sine of theta, because it's opposite that angle. All right, so now what do I have here? So I have this. Actually, I was going to simplify it and divide by the IB, but on the rubrics, the final answer was minus mgx sine of theta is equal to, I sub b d squared theta over dt squared. They didn't even, I was just going to put the I sub b underneath, so it was like d squared theta over dt squared, but you didn't even have to do that on the rubrics. So that was part A. That's part A, little I. Now for part B, I think that was that part. Yeah. So now for part B says by applying the small angle approximation to your differential equation, so to this differential equation, calculate the period of the bar's motion. So we want to find t. Now, if you have these programmed in your calculator, you already know my final answer should be t is equal to 2 pi times the square root of I over mgd. In this case, it would be x. So I already know, because I have this programmed in my calculator, my final answer should come out to be t is 2 pi times the square root of I over, instead of little m, big M, g, and instead of d, x. Now, if I just wrote this on the FRQ, I'm only going to get 1 point. So I don't want to get 1 point. I want my full 4 points on this, because this is how I'm going to get a good grade on the exam. So what do I do now? Well, that says by applying small angle approximation. So small angle approximation, okay, means, so small angle approximation means that sine theta is approximately theta. That's what the small angle approximation means. So what we're going to do is, when I do this, when I rewrite this equation down here, and I have negative mgx sine of theta is equal to I sub b d squared theta over dt squared, I can get rid of the sine. So now I'm going to have, so I don't have the sine. What I'm going to do now is I am going to move this IB over. So negative mg x theta over IB is equal to d squared theta over dt squared. So now I'm going to say to myself, wait a minute, I need to find the period, right? How am I going to, there's no period here. How am I going to find the period? What do I know about period? So I'm going to say, well, I know that period is equal to 2 pi over omega. Now that still doesn't help me because I don't have omega here, do I? I'm going to rearrange this for omega though and say omega is equal to 2 pi over t. The problem is I still don't have an omega here. So now I'm going to look at what I have here, and when I look here, what I'm going to say is, oh, I have d squared theta over dt. So d squared theta over dt squared, that's equal to negative omega squared theta. So now what I'm going to do is I'm going to take this and I'm going to substitute it in here. So now I'm going to say minus mgx theta over IB is equal to negative omega squared theta. Now, before I even go on, because I still don't have my period, I'm going to say, you know what? Both quantities have what? A theta. So let me get rid of that. Oh, there's an x on both, a negative. Let me get rid of that. So I'm simplifying as I go along. So now I have mgx over I sub b is equal to omega squared. So now at this point, I have omega in terms of t. I'm now going to substitute that in. So I'm going to have mgx over I sub b is equal to 2 pi over t squared. So I'll multiply that out. mgx over ib is equal to 4 pi squared over t squared. So now what I'm going to do is I'm just going to, I can cross multiply. I can do whatever I want algebraically. And again, so if I cross multiply, because cross multiplying is an easy way to get rid of the fraction. So I have t squared mgx is equal to ib 4 pi squared. So t squared is equal to ib 4 pi squared over mgx. So what I would do is, because I want to take the square root of both sides to get the period. So I'm going to have t is equal to the square root of 4 pi squared ib over mgx, but then I can pull out the 2 pi. So my final answer would be 2 pi times the square root of I sub b over mgx. So if I look at what I'm supposed to have up here, I see my final answer is correct. If I just wrote this final answer because I had it programmed, I get a point. If I show these intermediate algebra steps, if I have time, then I get 3 more points. So that's 4 points. It's all about time management. Okay, you have to say, well, I want my guaranteed 1 point, so I'm going to write that at the end. And if I have time and I know what to do because I know this, and I can clearly think how to substitute in to get to this, I'm going to do it.